Yeah, so one thing that I still find really amazing with the study of calcareous nanofossils is how easy and fast the preparation is. If you take this chalk of Denmark here and you reduce it into this fine powder, and then you put this powder in solution, dry this solution on a glass slide, and then use this glue, and then have the right magnification under the microscope, which is at least 1000. Then eventually you'll see that, which is our beautiful world of Late Cretaceous nanofossils. And obviously I took a nicely preserved example in natural light and in cross nipples. If you have the right type of sediment and preservation, like chalk of the Danish basin in the Must region, it's quite nice. Nanofossils, then they are really quite abundant. And such observations and studies of nanofossils now, they've been going on for decades because of the ease of this preparation. And we've seen the erection of many different zonations and age models. And that's one example of an age model here. And I think that these age models, they are really great, but they can also be a bit dangerous, as they give us a sort of false sentiment of security with the application of biostratigraphy. This, for example, it's not an up-to-date age model, as the Cretaceous Paleogene boundary is at 65.5 and not 66 today. But it's a good representation of an age model that was much used and well cited about 12 years ago. And I've chosen that one. You will see why later on. So what is the organization here? Well, you have this graph where we can see we have a number of nanofossil biohorizon, also some planktonic foraminifer biohorizon, in front of the magnetostratigraphy, the Crohn's, and an absolute age scale. And then, of course, associated to this, there was a table with absolute ages proposed for some of these biohorizons. I've shown Princey here or Miculamerus. And well, out of those, in particular, we're going to discuss during this talk this one here, the first occurrence of Miculamerus, this one, the last occurrence of Uniplanaria trifidus, and this one, the last occurrence of Ephilitus exiguus. So the reason why I choose this outdated age model and not the most recent age model is because this is the one that I had to confront my results with about 12 years ago when I completed the study of this oceanic site 762C in the Indian Ocean. So this site is really important, and it's great because it has a really good magnetostratigraphy. You can see the magnetostratigraphy here all along. We have all the magnetochrones. Sometimes there is some uncertainty, but still we have quite a good record. There were also some a lot of foraminifer bioevents, both benthic and planktonic foraminifer. And then we analyzed the carbon isotopes, and there is this very nice carbon isotope curve with this negative excursion across the companion masturbation boundary, which can be correlated worldwide. And then there is a number of additional small positive excursion that can be defined here, there, and they can also be correlated, those additional excursions. And then I also studied the nanofossils. So we have here the key nanofossil biohorizons and some additional ones on about 170 samples. So that's really quite a good record. In addition, the cores of this site, they present variations in color that we could relate it to the clay content, as you can see on this picture here. And we were able to demonstrate that they correspond to precession and eccentricity cycles. So that means that the site is really well calibrated also with orbital cycles. You can see here the filter output of the 100, and this is throughout the core. So this is a 100,000 years that is filtered out here. So I could have used that to calculate the ages of foraminifer and nanofossil biohorizons on this site. And I didn't dare doing that. And the reason why is because when you compare the results obtained on this ODP side to this conventional edge model that I presented you before, this is what you obtain. This is a picture you obtain. This correlation line all crossing each other. And even when it's not crossing each other, if you take, for example, the last occurrence of Eximius here, this is within Cons 32R over there. Here, this is well within C33, and so it's also not working very well. So there are several reasons for these really bad results. One reason is that there is a number of issues with this edge model. I think there were some things that were fundamentally wrong, like the last occurrence of Trifidus. I never found it in the middle of 31 hours. And the last occurrence of Parca constricta also is never that low into the Campania. So there were some things that were really not accurate in that edge model. But another issue was also bound to this particular site 762C that was situated in a transitional realm in between this austral assemblage and the tropical assemblage. And what happens across the late Campanian mass is that there are important climatic variations. And as you have cooling, warming, you have these oceanic fronts here that can move north and south. And I think this probably had a very strong influence. And in particular, in the transitional realm here, it could have been some sort of refuge where a number of species survive longer than in the tropical realm. That was one possible explanation. But that example brings us to a fundamental problem, which is calcareous plankton diachronism. And I try to list here all possible reasons for diachronism, and we will examine further several of these examples. A number of these issues have already been discussed by Claudia, like insufficient sampling, so I will not discuss that again. But we have very similar problems and solutions in the late Cretaceous. For example, reworking in the chalk in particular, this is something that is constantly observed. And one way to deal with that is to look at the consistency of occurrences. But there is also, for some taxa, smearing of a taxon due to rarefaction, and I will show you a very clear example of that. There are some preservation issues, and preservation issues, they can combine with a problem of gradualism, presence of intermediate forms, which is also a problem that Claudia mentioned in our talk. And finally, environmental pressure. We can have time transgressiveness due to climate change, sea level, or environmental perturbations. So that means in the end, we have to assess the reliability of biohorizons, looking at all these possibilities. This is an example here. It's a comparison of a number of the absolute abundance of a number of markers. This is a comparison between two sites that are approximately 250 kilometers away from each other, Stenswan and Rördel. They are together in the Danish basin, so in the Northwest European chalk. If you're looking at these patterns here, you can see, let's focus, for example, on Renartaetis levis. This species is supposed to get extinct in the early menstruation, in the lower menstruation, right? And you can see there is a constant flow of reworking with these inconsistent single occurrences over there. Once you are used to that, I think it's not too difficult to discard them and to consider that they have absolutely no stratigraphic value. But then you still wonder, what can you make of those ones, right? Which are still consistently, following the rest of the abundances. One problem is that, so if you take the last occurrence, for example, if you take the last occurrence of Coronum and you correlate it on the other side to the last occurrence of Coronum over there, let's say that was the last one, right? You do that, boom. And then you take the first occurrence of Maastrichtiensis here. You can see we're going to have a beautiful crossing of line, which obviously we don't want. So this is not the right method. So the right methodology is doing something very similar to what Claudia showed us to, is to take this first last common occurrence, or TC, and when you do that, you actually have no more crossing of lines. It's working much better, And you can also do that with rare taxa. I mean, those are relatively rare taxa. Viscodon coronum is relatively rare. Monomarginatus quaternarius is relatively rare as well. And even better, when you compare to carbon isotope curves of the two sites, and you correlate these carbon isotope excursions in gray, you can see that these top common occurrences, they occur, they follow very well this isotopic excursion. So there's no doubt that this is the right approach. Okay, but now the question is, can we solve all our issues of occurrence reliability with absolute abundances? So let's take the examples of Ephelitus eximius. The last appearance of the species defines the top of UC15. UC15 is here, right? And this is our nanofossil biohorizon. So it's important, right? It's the top of a zone that is defined by eximius. Well, now you can see we have these carbon isotope curves again between Tercis-Lebain, which is the GSSP for this companion menstruation boundary, Gubbio, which is the standard for the Tethys, and our Indian Ocean site. Let's look at where this biohorizon is recorded. Here it's there, over there. You can see the spread here of eximius. It's very, very large. The reason for this is because not less than 5 different workers worked on this section, all obtaining different results. If you take all their results together, it's over 35 meters, whereas they examined one sample every meter. So I think that tells already a lot. That reflects the fact, the issue that this taxon tends to be very rare towards the end of its range, and that makes results quite unreliable. But still, if we take the average over there, and we take the record here at Gubbio, the difference between the two is about 3 million years. So this is really a large uncertainty. This is bad for a taxon that defines the top of the zone. So yeah, how reliable is the last occurrence of eximius? Well, poorly reliable, and this is really quite an issue that we have to deal with. And the reason for this is because there is a smearing of this taxon due to rarefaction. So what we have is that we have first a decrease of its abundance during the late Companion, and then you can see over a very long time. And actually, this fact is largely confirmed by the Neptune database. If we examine the Neptune database, we can look here at the percentage of occurrence of all deep sea sites of this database. And there are issues with it, that database. Of course, we need to be cautious with its use, but still, this is really quite interesting to observe that when we're getting towards the end of eximius range, we have a progressive decrease like this of its occurrence of this percentage of occurrence in all deep sea sites. And if we compare to a species which have always found very reliable, Uniplanarius trifidus, you can see the pattern is really quite different. Look, trifidus, we have a very sharp drop, boom, here, right at the end of one bin, and if we take the middle edge here of this bin, it is indeed the edge of the extinction of trifidus. So we can show here with just this record of the Neptune database that we have a statistically reliable biohorizons and one that is very poorly reliable. If we go back to the same figure as before, we have isotopic correlation. This is where trifidus is, over there, and over there. It's always right above the companion menstruation boundary, always within the first 500,000 years from the boundary. I mean, 500,000 years is still some uncertainty, but it's much more affordable than 3 million years. Moreover, the last occurrence of trifidus has also been found in North Germany, in the German choke. It's right there, and it corresponds to it's exactly above the isotopic definition of the companion menstruation boundary. So it's great because then it allows us for an excellent correlation of the boreal and tropical zonations. So in the end, this is how I came up with a thorough revision of the boreal UC zonation and the tropical UC zonation. I revised the zone. I proposed to make two subzones using the last occurrence of Trifidus. For Eximius, well, we need to work much more on that, and I think it is very important that we produce many more records now of absolute abundance of the species to better understand where we can possibly position a last common occurrence. Other examples that are again similar to what Claudia mentioned for the Cenozoic is the problem of taxonomy. But in the case of the late Cretaceous, taxonomic issues, they often combine with preservation issues. The best example that we can give is that of Renartitis, which has two clear distinct species, Renartitis entophorus, so this is this guy here, and Renartitis levis, which can either small or large forms. The issue is the first occurrence of Renartitis levis, given right here in the Neptune database. This first occurrence is used in the North Sea for the definition of the subzone UC14II in the Fritzen et al. Scheme. The problem with the North Sea chalk and the chalk in general is that the preservation is rarely very good. There's always some recrystallization. And as recrystallization occurs, the inner cycle of entophorus, this inner cycle, tends to be overgrown and fills the central area, fills the pores, making it look like levis. So this is the issue that we have here. On top of that, there is actually some gradualism. There is an intermediate form between entophorus and levis, which is elegans, and it has been defined by Atner and Wise. And the definition is like the pores are not as open as entophorus, and then there are also some distinct features of the calyx, but we can't really see that because most specimens lack intact stems. So you can see the issue here, and what makes this first occurrence pretty unreliable is the fact that we have intermediate forms, and also the fact that we have preservation issues with this overgrown of entophorus. But finally, our last issue is with Calcareous plankton diachronism is a textbook example of biostratigraphy and biogeography. This is maybe a concept here that I've drawn that is more commonly presented for invertebrates and, for instance, for nectonic organisms. But essentially, there is a distinction to make between a biozone that we define in one section, which is bounded by the first occurrence and the last occurrence. So that would be the biozone. If we take a taxon range biozone, that would be a biozone at one particular latitude here. And there is a distinction to make with this biozone and something completely hypothetical that we can call the chronozone. And if we want to define the chronozone, well, the chronozone is defined at the base by here the exact date and place of the first appearance of the taxon, and at the top here by the exact date and place of the extinction of the taxon. And these two, they are hypothetical. If we really want to get them, then we would have to analyze all possible sections all around the world, which is of course not possible. And I think that remembering that there is this distinction between the biozone and the chronozone is quite important. I've heard several times the idea that this example should not apply to microscopic algae, that should essentially spread very fast throughout their range of preferences after their first appearance. But here I must disagree, because there's one very clear case of a time-transgressive colonization of different latitudinal domains by Micula murus. If you examine this graph here, it's a graph that I recently updated. I've shown the maximum possible interval of uncertainty for a number of sizes. This uncertainty was calculated with the uncertainty between two samples analyzed for nanofossils, and also the uncertainty of the magnetochrone of the reversal. So if you take this uncertainty, well, you can still see that we have at least maybe 4 distinct events, with a very first occurrence here in the equatorial Atlantic in the top of C31R, then another one within C31N at low latitudes of the North Atlantic, tropical Pacific, and Eastern Tethys. and also in low latitude of the South Atlantic. And then there's another event within C30N, which is in the mid-latitude of the South Atlantic, mid-latitude of the North Atlantic, in the Indian Ocean, in the central Tethys. And then finally, later on, much later on, we have this colonization of the Northwest European Chalk Sea over there. So this is quite interesting, and of course, well, Micula Moros is also a marker for the late menstruation. So we need to be really aware of these patterns. There's no doubt that one of the reasons for these patterns is because the species had a strong affinity to warm temperatures, as one can see on this paleobiogeographic map. And the paleobiogeographic map of Moros, I mean, it even shows some very interesting features when we look at the presence versus absence. Absence over there, it's present also here on the shelf of the US. So that means that you can see it's delineating some currents that we know today. They are very similar to some of the currents we know today, like this Proto-North Labrador currents, or the Canary currents, or the Falkland current. The strange thing is that the colonization of middle latitude by Micula Moros at this one here, this event, at 67.7 million years, it doesn't occur during a warming event. It occurs across the transition from the mid-menstruation warming here to the late menstruation cooling. And this is really counterintuitive and difficult to understand. The last colonization here, this is much more logical because it occurs in sync with the Deccan warming, this greenhouse warming caused by Deccan volcanism. So here we understand it's getting warmer, and we have the species going higher up in northern latitudes. Okay, this graph allows me to mention fast another issue with respect to paleoecology. The result that you see here, you see results on the oxygen stable isotope on forearms. Here, bulk carbonate isotopes following very nicely the same trends. And then we have this nanofossil temperature index that are also following similar trends: cool, warm, cool, warm, cool, warm. And how this was built? Well, this because there was some really abundant cool water markers of high latitude species like Calcareous magnificus or Acrangoscilla cymbiformis. And there are some very clear opposite patterns between Wasneria barnesi and this high latitude taxa. Wasneria barnesi, you can see its abundance is peaking during the warm event here. But now if we compare to the equatorial Atlantic, in the equatorial Atlantic, if we look at the same interval, we have much lower abundances of our high latitude or cool water taxa, but still you can see that when we combine their abundance, they still delineate these two cooling events, the early menstruation and late menstruation cooling. But if we look at Barnesi, we can see that the patterns of Barnesi, they do not respond to this climatic variation. They respond to something else here. So why is that? Why is it that in one site we have Barnesi responding very well to temperature changes, and in another it doesn't? Well, I think that the reason is because we have this picture here on this graph of the preference of Barnesi. This, I've tried to report here hypothetical environmental conditions of the Chalk Sea. They are ultra oligotrophic, and they are much cooler, of course, than tropical latitudes. And these are the environmental conditions of the western North Atlantic in gray. And what happens this graph represents with the color from cool to warm the hypothetical relative abundance of Barnesi. And you can see that when you do that, what happens is that here, when you are towards the edge of the ecological preferences in temperature, the sensitivity of Barnesi is essentially to temperature. Whereas over there, the sensitivity of Barnesi in the tropics will be essentially to fertility, so to change in fertility. So that leads me to my conclusion, my take-home messages. First, the reliability of biohorizons needs to be assessed, and I agree with Claudia and Nini that we need to use absolute abundance patterns, but I would be more cautious with the term of standardization, because standardization is going to be difficult we have different methods of preparation, and we have different abundance depending on the period of time that are studied. So it's not going to be an easy task. Integrated stratigraphy is the key. If you want to solve issues like diachronism, I think this is really important. Plankton diachronism is something real, but there are various reasons. And it is important, if you observe plankton diachronism, I think it is really important to ask yourself, okay, why is that? Why do I ask that? Can I try to find out the reason? And finally, I think that there is a danger in the strict application of environmental indices. Distinct environments can show various assemblage response to global climate change. And this is why I think we should always first assess changes in the assemblage through multivariate statistics, such as principal component and cluster analysis, before applying temperature index or fertility indices. So thank you very much, and thank you very much for inviting me, and many thanks for preparing this fantastic initiative by the INA and Aurora Communications.